Okay, so we're busy with hidden Markov models, and there is this classic way of explaining hidden Markov models that looks at three specific questions: the marginal probability, the most likely state sequence, and then learning the parameters of the model. And what we actually did in the last lecture, and we finished this, was we looked at this second problem, the one of finding the most likely state sequence. So I give you a hidden Markov model, I tell you its parameters, I give you an input sequence, and I ask you what is the most probable path through this hidden Markov model given that observed input sequence. And you did that using an algorithm called the Viterbi algorithm. Now, I start with problem 2 because if you understand problem 2, then problem 1 is easier to understand. Okay, and then problem 3 is very easy to understand in principle. Okay, so we're going to go to problem number 1 now, which is the marginal probability. And the question here is, given an observed state sequence, so again, I give you a sequence of things, of observations, maybe words, and now I ask you, what is the overall probability of observing this sequence, this observation sequence, given that you know the parameters of the hidden Markov model? Basically, what's the marginal probability of that sequence? Okay, does that make sense? Spoiler, the algorithm that we are going to come up with for doing this is going to look very, very similar to the Viterbi algorithm with one big change. So let's just think, why would we want to know the marginal probability of some sequence? Why would I want to know, P of theta of an observed sequence x1 to t? Okay, now I'm going to use a little example from speech recognition to just explain why we would want to do this. So in speech recognition, this is a very, very simplified speech recognition problem where we have a little waveform that comes in, and I want to know which phone occurs in this waveform. Is it a E, a R, or a E? Okay? Which one of these three phones is in this little snippet of audio? Now, in speech recognition, what normally happens is you first convert the audio into a sequence of vectors, acoustic feature vectors, basically. And I don't want to go into the full details here, and if you don't know about this, then that's fine. But basically, what you would do is you would take a little snippet of audio and capture the acoustic or the frequency content in that little window. And that would give you a little vector x1. Okay? Then you would move that window, you would get a second window, and that would be a little other vector x2. Okay? And you end up with this little sequence of vectors up to x capital T. Okay, now these vectors are continuous, so your hidden Markov model will look a little bit different. The ones we've looked at up to now, they were all discrete hidden Markov models, so they output something that's categorical as its emissions. But in this case, you will have to model something continuous. Okay, so your emission probabilities, your emission distributions here, the thing that kicks out, in this case, a little blue vector here, that emission probability will have to be a Gaussian mixture model, or a Gaussian, or something like that, that can capture the properties of a continuous vector. I've trained 3 hidden Markov models. I didn't tell you how I trained them, but I've trained them, and I give you their parameters. So I tell you, this first hidden Markov model here, I tell you its parameters, and its parameters is theta AE. This one has parameters theta AH, R, and this one has parameters I. Okay? And now what we might want to do is to figure out which one of these 3 phones is occurring in that sequence. We might want to push the sequence of vectors through all 3 of these hidden Markov models, and then we pick the one with the highest marginal probability for that particular sequence of observations. Okay, does that make sense? Okay, I'm ignoring something here, like to make it a proper classifier, you need to also just see if some of these phones are more likely to occur than the other ones. But if they're equally likely to occur a priori, right, beforehand, then you can just compare the scores that you get out of all 3 of these hidden Markov models, and then you say this is the sound that occurs. Okay, let's quickly think, how does that compare to Viterbi? Okay, so what does Viterbi give me? Just remind me.
Most likely state sequence.
Okay, the most likely state sequence. So how is the that's right. So Viterbi gives me the most likely state sequence. So if I give you this sequence of vectors, Viterbi can answer the question, what is the best way to move through this hidden Markov model? Should I go there and then linger in this state a little bit and then jump to this state and then go to end state? That might be one path. Another path might be dunk, 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 linger, 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 linger out, dunk, okay? But with Viterbi, you'll also get a score basically for that little path. I denoted it as P hat in the previous notes, okay? So you could also, does that make sense? So what you could do is you could also do Viterbi here, Viterbi here, Viterbi here, and collect the 3 scores that you would have gotten, okay? PAE, PR, PE, okay? And then select the best one. That would be an alternative. But what Viterbi ignores is that there's actually more than one path through each of these hidden Markov models. And what might happen is maybe one has a pretty good P hat, but actually if you consider all the possible ways of going through this hidden Markov model, then maybe another model actually gets a higher marginal probability overall if you consider all paths. Okay, so I hope that starts to give you an intuition for the difference between this marginal probability problem and Viterbi. Viterbi gives you the single best probability through my hidden Markov model. Okay, and that tells me something, but it doesn't actually capture the overall probability of moving through this thing. And the overall probability, because there might be other paths that if we sum up all the possible ways of going through this hidden Markov model, will actually give me a better overall marginal probability.